Good afternoon, everyone. Welcome to our third and final press conference for today, and it's on contaminated waters, pollutants in rivers, and groundwater. And we'll have the three presentations, one after the other, and then in the end, we'll open the floor for questions from journalists here in the room or those watching us remotely on the live stream. Taking part in this press conference, we have Francesco Bregoli, who is a postdoc researcher at the Department of Water Science and Engineering at the Delft Institute for Water Education in the Netherlands. Then we have Marina Strokal, who is a postdoc researcher at the Water Systems and Global Change Group at the Wageningen University and Research in the Netherlands. And finally, we have Caroline de Meyer, who is a researcher at EAWAG, I don't know, HEOAG, the Swiss Federal Institute of Aquatic Science and Technology in Switzerland. And I'll hand over to our speakers now. Thank you.
Thank you, Barbara, for the presentation, and thank you for the invitation. I'm very glad to be here. Thank you also to the EGU General Assembly. So I'm going to present you the work that have been done in the Catalan Institute for Water Research 1 year ago with my former colleagues from that institute, although I am here thanks to IHE Delft that is supporting me here in EGU. So the work is about the fate of pharmaceuticals in fresh water, with a global model for decision making. I'm going to guide you to in a short presentation to explain what we have done. So it is known that we have a high pharmaceuticals consumption in the world that may endanger ecosystems. If you see this flow, we can see that there's several steps from the consumption to disease, let's say. So when a drug is consumed, then a part of that is absorbed by the organism, and a part is emitted, and then can be collected and treated in wastewater treatment plants. A part of this is removed. A part of these contaminants is removed in the treatment, but a substantial part is poured in the ecosystems. In particular, we are focusing here on freshwater ecosystems. So there's some studies that have observed concentration up to 100 times the toxicological limits of some compounds. So there's a tangible threat, let's say. And the ecosystem, of course, the ecosystem services are also very important. They also are also able to reduce the presence of pharmaceuticals in the river networks in this case. So our model wants to account what happens to the pharmaceuticals in all those steps that I showed to you. And particularly, we will also look into the current scenario, so what is happening right now in the world, but also taking into account the future scenarios. So we include in our calculation also climate change, population growth, and we propose some mitigation strategies, particularly on reduction of consumption and in technological improvement, so in the treatment improvement, let's say. I'm going to show you some pictures for the particular case of diclofenac, which is a painkiller, very common used in all around the world. And here you can see in this image that the consumption per capita is not even distributed. But there's some countries that are consuming more than others. You can see the consumption up to more than 1 gram per year per inhabitant. However, if we go to the following picture, we can see that the most populated countries are the ones that are, let's say, emitting more in this case, diclofenac. So you can immediately see that our more populated countries like India, China, or Brazil, that they have a big load of pharmaceuticals in the environment. So in some cases, more than 100 tons per year. Another important thing to say is that the wastewater is not equally treated in the world. So if you can see also in this map, you can immediately see the red countries that are not treating the wastewater. The level of treatment of wastewater is sometimes lower than 20%. And that is happening in developing countries, especially. So South America, Africa, and some countries of Asia. If we go a little bit on the results of our model, here is the same picture of before with some data inside. Those are already some results of the model. So you can see the numbers. In green is the numbers related to the world. In blue are the numbers related to these macrocontinents that I report here, Europe and Middle East together. And in red, Asia and Oceania. And after the consumption, which the data are there, 2,400 tons per year worldwide for the case of diclofenac. Part of that is emitted, collected and treated in the wastewater the wastewater treatment plant. You can see immediately that there's a part that is removed. The part removed is often low. So 7% worldwide, let's say, but when you go to Europe and Middle East, it's 15%, so a little bit more than the average. And for Asia and Oceania, it's only the 3%. If we go to the capacity of the mover of the ecosystem services, we can see that they are quite high compared with the treatment. Of course, the network, in this case, freshwater and river network is very big in the world. So we can see that mainly around 20% of the load of the emission, is removed by the ecosystem. Finally, we can see that in the river still arriving a big amount of pharmaceuticals. So, sorry for this slide, a little bit small. But what I wanted to show you is that currently the model predicts that the 0.8% of the river network is affected, in the sense that is showing higher concentration levels. For instance, if we look to the European Community Watch List limit, which is 100 milligram per liter for the diclofenac, this is so around 0.8% of the river network shows more than this, a concentration higher than this limit. If we include the future changes, so climate change and population growth, we can see that the affected network is increasing in length of 65% respect to the current scenario. If we introduce certain mitigation measure on the consumption, so if we lower the consumption, in this case we propose a reduction of 10-12%, which is also quite arbitrary, but we see that there's a high response, so the reduction is substantial. And the technological improvement seems that are not enough to reduce substantially the concentration limits. But if we include all the mitigation, so the consumption plus treatment improvements, we can see there's a synergy, and we might have a reduction of almost 30% respect to the future scenarios without mitigations. So the main conclusions of this work is that the pharmaceuticals' highest concentration can be found in fresh waters. I didn't show any pictures, but those hotspots are close to metropolises and where is densely populated areas, and particularly, but not only, in developing countries. The other main conclusion is that future scenarios analysis suggest us that the technological improvement alone will not solve the problem completely, and therefore we should include a reduction of consumption strategies to achieve a better result in the freshwater. And for me, that's it, and I'm open for questions later. Thank you.
Good afternoon. I am Marina Strokal from Water Systems and Global Change of Wageningen University and Research. And in my group, we focus a lot on trying to understand the causes of water pollution, but also explore solutions for reducing water pollution. And today I focus on river pollution from sewage systems. So on these pictures, you see examples of water pollution worldwide. And many rivers in the world, they have more than one pollutant. They have multiple pollutants. For example, plastic, you can see on this picture, chemicals, nutrients resulting in blooms of harmful algae, and then fish can die. But also pathogens happen in river systems. Pathogens are microorganisms that make people sick, for example, diarrhea. As a result of these multi-pollution problems, aquatic ecosystems suffer, but also water is not longer available for human use. So our message is that increased sewage connection will increase river pollution. And why it happens, I will show you in a few minutes. We argue for multi-pollutant assessment to be able to identify effective solutions. And there are three important reasons why we need multi-pollutant assessment for effective solutions. The first one, that many pollutants come to rivers from common sources, for example, from sewage systems in cities, but also from agricultural activities. The second reason is that there are also interactions. Pollutants may interact in aquatic systems with each other. And the third reason is that pollutants cause multiple impacts. So we use water, polluted water, for different activities. And effective solutions, if they are effective or not, it depends whether all these interactions, common sources, and impacts are accounted for. At Wageningen University, we develop a multi-pollutant modeling framework to assess river quality. And the circle in the middle illustrates a hydrological model, and smaller circles around show individual models for individual pollutants. So we have models for nutrients, river temperature, oxygen, plastic, triclosan, and triclosan is an antibacterial agent that you can find in soap when you wash your hands, and then it enters sewage systems. And in fish or any aquatic organisms, it can cause hormone disruptor. And pathogens, microorganisms. You don't have to look at all the details on the maps, but you may have observed that on many maps you see yellowish and reddish colors. And those colors indicate problematic areas, areas with water pollution problems. And at Wageningen we try to integrate these models together to say something about hotspot areas of multi-pollutant problems, and then to identify effective solutions for them. So now I would like to show one example for river pollution from sewage systems where the integrations of models took place, and for the future year 2050. In the future, it is likely that more people will live in cities. And that means that also more sewage connection will be, so more population will be connected to sewage systems. And this graph, this map shows the results when treatment in sewage systems is improved only slightly. And reddish and yellowish colors indicate that more pollution is expected in 2050 than today. And greenish colors, there are a few basins on top, show that those areas will have no pollution or less pollution in the future. And this map shows when the treatment is improved to a large extent. And improving treatment here, you can imagine that European standards are implemented. So the treatment efficiencies are very high to remove pollutants. And if that is implemented in 2050, then many river basins that you saw in yellow, they will change their color to green. And that means that those river basins become less polluted in 2050 than in 2010. However, there are a few exceptions. The rivers in Africa and South Asia, where still rivers may have more pollution than today. So the message that I showed in the beginning is that increased sewage connection will increase river pollution if the wastewater is not treated. And I would like to emphasize that sewage connection is a very good thing to improve sanitation in urban areas, but it should come together with improved treatment. And future hotspots of multiple pollutant problems are in river basins of Africa and South Asia. Thank you.
So, thank you. So my name is Caroline de Meijer. I'm a geologist. I'm working as a postdoc researcher at EAWAC, so the Swiss Federal Institute of Aquatic Science and Technology. And together with our partners at the Uni in Lima in Peru and at UFAM in Manaus in Brazil, we are investigating the presence and distribution of natural contaminants in groundwater resources in the Amazon basin. And actually our main finding is that in certain parts of the Amazon basin, contain arsenic, manganese, and aluminum at concentrations that are potentially harmful for human health, which means that long-term exposure by consumption of this water with such a high concentrations of these elements might result in severe health problems. So as we can see, so we found actually, especially for arsenic, we found up to 70 times higher values than what is accepted as a maximum limit by the WHO for drinking water. Now, why did we go to the Amazon and what is new with this? Well, actually it had been suggested that there is a potential for arsenic contamination in groundwater resources of the Amazon basin, but it has not been thoroughly studied. So when we were looking for data to confirm this hypothesis, we didn't find many data points. Actually, we even realized that there's very little known about the chemical quality and especially about the trace elements in groundwater resources of the Amazon basin. And this, despite the fact that many people rely on groundwater as a source of safe drinking water in this large region, both in rural as in urban areas. For example, here are two types of wells, like we have these hand pumps installed by NGOs, or we have also electric pumps in community where water is pumped into a reservoir and then distributed through taps to the houses or to central places. So we wanted actually to answer this question, is there indeed arsenic in this groundwater? And what other elements do we find? Are there other elements of concern? And where do we find? So we went to the Amazon basin. Now, the Amazon basin is huge. It's taking almost 30% of the South American continent. So we did not sample each well, and that was also not our aim, but we chose our sampling areas as such that we could actually get the maximum of information on a relatively small area. and that we had various environmental settings on the same place, so that we then could extrapolate our results to a larger region. Now, in a first pilot study, we went to the Western Amazon in Peru. We chose there 2 areas. And what were the results? So, as I said, we found indeed arsenic concentrations very high in this groundwater, but not only. There was also high concentrations of manganese, and in other wells we found high concentrations of aluminium. And we could show that actually the distribution of this contaminated groundwater sources is directly linked to the geology and to the river type. So this is a sketch of this pilot study that was published a couple of months ago from Peru. So what do we see? We have actually manganese and arsenic-rich water in the sediments that are deposited by the so-called whitewater rivers or Andean rivers, like, for example, the main Amazon River. So these rivers, they originate in the Andes and are transporting huge loads of sediments, which are partially deposited along their way in the floodplains. And actually, groundwater in these sediments are naturally enriched in arsenic and manganese. Whereas aluminum we find in other types, so that we find close to the blackwater rivers. These rivers, they do not originate in the Andes, but in lowland Amazonia. Like, for example, the Negro River in Brazil is the largest one. Now, there we have typical sands where the groundwater is acidic. And the acidity of this groundwater makes that aluminium get dissolved from the sediments and accumulated in the groundwater. So wells that are tapping this groundwater in these sediments contain high concentrations of aluminium. Now, after this study, we wanted to investigate more where exactly. So we have this contaminated. So we did more sampling campaigns. We, not only in Peru, but also in Brazil, we went to the central Amazon, close to Manaus, along the Amazon River, but also on the Madeira River, another large whitewater river. We spent actually weeks in a boat going from community to collect water from tube wells. And this is still work in progress. But what we see in our preliminary results is that it's going in the same direction. So these contaminants are not local. It's a global, it's a basin-wide problem. And we see that really in this, close to these whitewater rivers, we have this arsenic and manganese. And also this blackwater, we can have these high concentrations of aluminum. Now, are people aware of this, the occurrence of these elements? Actually, no. When we look at this water, so this is water that we are sampling that contains some high concentrations of aluminum. And as you can see, this water is very clear, and you cannot taste or smell aluminum. So the people are just drinking this water as such. Whereas arsenic and manganese-rich water, that can be, there it varies. So we have sometimes very clear water, although there are high concentrations, but depending on other substances like dissolved humic acids, there we have some yellowish or greenish color. But the good thing with this water is that it often contains also high concentrations of iron. And iron you can smell or taste, or you can also see it, because when the water is pumped to the surface, then it gets in contact with the air, and iron will get oxygenated and will precipitate and form this typical orange crust, as you can see on this image in this reservoir. So people, they don't like this taste of iron or the fact that it's giving this color. So what they do is that they let the water settle in a bucket or in a reservoir for several hours and then take the rest of the water. And the point is that with this iron, also a part of the arsenic is actually co-precipitating. It's not always the case. It depends how much iron is also in the water. But in most cases, what people are consuming are at least already lower concentrations of arsenic. But the manganese is not precipitating with the iron in most of the cases, which means that people are consuming such a high concentrations of manganese when they consume this water. So I think with our study, it's important that we actually show the presence of these contaminants in groundwater resources that are used as drinking water, and that now our results can be used actually to take action where needed. Thank you.
Thank you very much for your presentations. We'll now open the floor for questions. Are there any questions from the journalists here in the room?
Thank you. Marlo Hood with AFP. I actually have one for each of you. Francesco, did you sort of test the power of your predictive model against sort of data from the real world collected in the field? And if so, could you describe that a little bit? Caroline, how did you get onto the trail of this story? I mean, how is it that you started in Peru, and how did it come to your attention to begin with? And then for Marnia, you emphasize the importance of a multi-pollutant approach to this problem, but to what extent have studies actually been made of the interaction of pollutants? And if, as I suspect, not very many, could we be underestimating, in fact, the level of pollution as a consequence?
Starting?
Yeah.
Okay. So thank you for the question. So basically, we collect a number of studies. So finally, we had 1,400 point measurements distributed in the river network, in the global river network. So we tested the model against those observations. Like the thing is that I have to say that those observations are not like well distributed around the globe. So of course, where the problem is more sensitive, or probably in more richest countries, there's more studies. So we have lots of studies in Europe. We have a number of studies in North America. We have a number of studies in Asia, but we don't have studies in many parts of the world. And this is also why we start this work to build a model able to spot other problematic points around the world. Well, within the problem, the common sense, or common problems of global models, yes, we have a good agreement with the real observation. But of course, when you want to see the problem in detail, you need to reduce, of course. Yeah.
Okay, about multi-pollutant assessment. This multi-pollutant framework, actually we have one study available, which is published in the UNEP report, and the framework that we are proposing, it's actually building on that one too. So, but in general, the multi-pollutant assessments are very much limited in the knowledge. So we find a lot of studies analyzing the impacts and pollution levels of individual pollutants, but not combining multi-pollutants together because of their interaction and common sources. So this is really under development in my group. And regarding interactions that we may underestimate pollution levels, that's a very good point and difficult to answer because there are studies, local studies or experimental studies that do that study some interactions in the lab, for example, like plastic and microorganisms that can attach to plastic and then settle down. But on a global scale, to my knowledge, I don't know studies that exist that can account for interactions between pollutants on such large scale. And yeah, I cannot answer whether we underestimate or overestimate. This is something that we should do more work to investigate. And this is what we start in my group. We start with first integrating the sources of pollutants together. So today I showed sewage systems, and it's still under progress. And we are working on other sources, also diffuse sources. And then we'll link that with hydrology, and we will try to also account for interactions between pollutants in water systems.
So thank you. So if I understood well, you were asking why did we go there and why first Peru and then Brazil? Yeah, so actually I have a map that I can show. This is actually it's a probability map that was modeled for arsenic in groundwater due to reducing aquifer conditions. So that's one of the processes, natural processes that makes that arsenic get accumulated in groundwater. And you can recognize some countries that is well known here in Southeast Asia, but also immediately you see in the Amazon this red spot, which means high risk. But this is a model, especially for here. There was no data involved in this. So we wanted to check if this model is correct. And not only, there were also other researchers that suggested it, because actually the Amazon is quite similar to this river basins or deltas where you have this arsenic-rich groundwater. So why first Peru and then Brazil? That was just a question of funding. We first found actually seed money to go to Peru, and then there was a call for collaboration with Brazil. But in Peru, when we started really looking like at the geology of Peru, we realized that there was this city in Peru that's called Iquitos, which is quite particular. It's the largest city in the world that you can only access by plane or by boat. But also because it's lying actually at the confluence of a whitewater river, actually the Amazon River, and also Blackwater River. So there, in actually a short distance, we could really get already various environmental settings and look what elements we get in the groundwater. Oh.
Thank you very much. Are there any additional questions?
Yes, Milan Ilic, Daily Paper, Slovenia. I have one question for Dr. De Meyer. Is there any practical solution for the population there? How to eliminate those, how to say, excess amount of arsenic, manganese, and aluminum from the water?
Yeah, so as we saw in other countries, actually, there are some simple treatment systems, like, for example, for arsenic and manganese, like sand filters that can be installed, or as there's already quite some iron in the water that helps. By aluminium, you should think of a system that certainly already exists, or also to increase the pH to let the aluminium precipitate. And another thing would be actually to look for safe aquifers, because we see that there's also aquifers like in other sediments where there are no contaminants. So, and we have to increase the hydrogeological knowledge actually to determine where these aquifers are. They can be actually just be lower. So you have to drill deeper and then get access to this aquifer. But our partners at the Uni in Peru, they just got funding actually to develop treatment systems adapted to the local conditions there.
Thank you. Any further questions?
Tim Kalvelage, I'm editor for Spektrum der Wissenschaft, the German edition of Scientific American, and I have a question to both of the first two speakers. And well, I'm wondering about the costs of wastewater treatment. And so, Francesco, you said that improved wastewater treatment could help to mitigate pollution of freshwaters by bioactive compounds, but as far as I know, even in highly developed countries, there are no dedicated stages in wastewater treatment plants typically to remove those compounds. And so I imagine it would be highly costly and increase costs of freshwater for Europeans or also other people around the world. And similarly, Marina, you showed those two maps where Central Europe all of a sudden changed from yellowish red to bright green by 2050 due to improved wastewater treatment. But already now, I mean, a lot of wastewater treatment plants in Central Europe are at the limits of capacity due to, for example, nitrate pollution of fresh waters. So also that will be highly costly. And have you, either of you, looked at what that would mean in terms of prices, or what would we have to invest actually to reach those targets?
So maybe my colleagues have more detailed answers. For sure, it's very costly. Actually, I think that is one of the things that we want to look in the future. How much it costs including this treatment, and if it's feasible or not. At the end, our solution is reduce the consumption. I think, if I'm not wrong, in Central Europe, I'm thinking about the case of Switzerland, where they have a very advanced treatment plants. In some cases, they are able to reduce substantially some of the pharmaceuticals, but some of them are persistent. It is nowadays not possible to eliminate. So the only answer that I have is not reduce the consumption. And I think that some countries have already done some effort in reducing some of the pharmaceuticals. I have in mind France, for instance, that made several campaigns to reduce antibiotics and were successful. So those are way cheaper than implementing new wastewater treatments. But maybe about the exact number and costs, do you have some answer more?
Yeah, well, I would agree with my colleague that it's indeed costly. I personally didn't look at cost of treatment types, but at the university where I work, we have a group of people who are specifically focusing on developing innovative technologies to treat waste, and they look at waste as a source, but not as a waste, as a resource. They look at waste. So they develop technologies to actually recover, for example, as you mentioned, nitrogen pollution. So they have those technologies. There are actually a lot of technologies already available. And they make pilot studies to test them also in specific cities. And I think it's a matter of time when we go from those pilot studies and upscale them to a larger scale. But I would agree that it will cost. But 2050, it's quite some time to go, and the technologies are being developed very fast and getting cheaper and cheaper. So we never know what will happen 2050.
Thank you very much. Are there any additional questions from the journalists in the room? No? If not, we'll finish here. You are welcome to book one of the interview rooms we have available on the site. Our next press conference... Oh, sorry, we do have one from the chat. No, not from a journalist. So we'll finish here. And I'll hope to see you tomorrow for our press conference at 10:30 on Forests Under Pressure. Thank you very much for your presentations. Thank you all for coming.